Okay, so we are going to move on to a comparison theorem. And what a comparison theorem is it is just finding another graph that is close to, that always stays on the same side of a function. So in this case, we have f of x and we have g of x. Now, f of x is always going to be less than g of x. So if our function g of x, let's say we are trying to find out what the area under the curve of g of x is. Well, if we look and the area under the curve of f of x is positive infinity, then the area under the curve of g of x must also be positive infinity. So we can use information like that by finding a graph that we can integrate and then comparing it to one that we cannot integrate. So let's look at the actual theorem here. So let f of x and g of x be continuous. Assume that f of x is between 0 and g of x. So what they're saying, if you're trying to find the integral from a to infinity of f of x, you can change that to the limit. We've already talked about that. And if that limit of f of x is equal to positive infinity, then the area under the curve of g of x must also be positive infinity, because g of x is always bigger than f of x. Also, if the area under the curve from a to infinity of g of x is equal to the limit as, so just changing it to the limit so you can integrate it pretty much. If it is equal to L, then f of x is equal to m for some real number where m is less than or equal to L, because f of x is less than, always less than g of x. So let's look at some examples of what we can do to use that theorem. So I'm just going to talk about this one just a little bit. So on this function, determine whether this, so this is the equation that we want to find the integral of. We're going from 2 to infinity, but that's a pretty big equation to integrate, and we would have to go through, do all of our partial fractions and everything like that. But we can get a really good idea of what's going on if we just look for a simpler version. So this equation, the x to the 8 plus 4 over x to the 10th, if we looked at a simpler version of that, let's look at 2 to infinity of x to the 8th, because if we're going on to infinity, this little 4 out here at the end isn't going to do very much for us. And then over x to the 10th, now this equation, is it going to be bigger or smaller than our original one? And how are we going to figure that out? Well, the numbers, the values that we're plugging in for this, the ones we're looking at, our interval is from 2 to infinity. So from 2 to infinity, those numbers are just going to get bigger and bigger and bigger and bigger. Well, in our numerator, we're only going to be plugging numbers in for the x to the 8th. X to the 8th is in both of them. Yes, there is a plus 4 here, but that's going to mean nothing by the time we get up to 1,000, 1,000,000, all of those really big numbers, and then taking the 8th power of it. 4 is not going to make any difference at all. So let's look at our denominator. We have x to the 10th in our new equation, but this one here also has a plus 8x to the 12th. Well, we're going to be plugging these values in for that x. But what is that going to do? It's going to make this value bigger, which is going to make our denominator bigger, which is going to make the whole problem smaller. So this equation that we have here is actually always going to be greater than this equation right here, our original one, from 2 to infinity of x to the 8th plus 4 over x to the 10th plus 8x squared plus 29. So this equation right here, we can simplify that to 1 over x squared. So let's start looking at the questions that they've asked us here, because we are not going to integrate this. Don't worry about finding any of these integrals. We're just doing the comparisons. So use a comparison to of d of x over x to the p for a positive integer p. The smallest p-value that we can use, well, the p-value is representing the exponent in the denominator. So that's going to be a 2 in this case. So the smallest p-value I can use is 2. Now, there's little circles here that you can choose which one of these is true. Is this equation here greater than our original, or is our comparison equation less than the original? Well, we decided right here that our new comparison equation is going to be greater than our original. Okay, so we are going to choose this sign right here. Okay, and not the less than. So this makes a true statement. Also, it wants to know what happens to this function right here. Does it converge or does it diverge, as we are going to a very, very, very large number? So our interval is between 2 and infinity. So what happens when I plug in 1 million? This is going to be getting closer and closer and closer to 0. Okay, and then this one here, if it's going to sandwich it in there. So if this is getting closer and closer to 0, then this one must be also. Okay, so that means that this converges and this converges. Okay. All right, on example number 9, we need to determine if this integral, or this equation right here, the integral of this equation is divergent or convergent, and we want to do a comparison of it. So we want to know an equation in this format that we can compare to this equation. Now this one isn't as easy as the last one that we did. So what we're going to do is we're going to start with a skeleton of this equation. And I'm going to pull out something that I know about the domain, or the range in this case. I'm going to pull out this cosine 0.5x because I know that I can put boundaries on that. And I'm going to start with that and then slowly build my equation back up so that we can use that comparison theorem. So I've got the cosine of 0.5x, and I know, because my amplitude is 1, and we learned this last year, that it is always, the greatest value it can take on is 1, so it's always going to be less than or equal to 1, and it's always going to be greater than or equal to -1. So because of my amplitude, I know that. Now, let's start to build this equation back up. Next thing I need to do is add 2.5 to my equation. If I'm going to add 2.5 to the middle, I also have to add 2.5 to all sides of my inequality. So now I'm going to have positive 1.5 is less than or equal to 2.5 plus cosine of 0.5x, which is less than or equal to 3.5. Okay, now the only thing I have left to do is to divide by x to the 1.5. If I do it to my middle equation, I have to do it to all of the other equations as well. So what I have been able to show here is I have shown that this equation, given above, is always going to be in between 1.5 over x to the 1.5, or less than or equal to 3.5 is less than x, or over x to the 1.5. Now this equation, the format that they give me, doesn't give me anywhere to put a constant in the numerator. But I know that 1.5 is greater than 1 over x to the 1.5. So I can confidently say that I can compare this to the equation 1 over x to the 1.5. And then whatever happens to this equation, it's going to be a boundary to our original equation that we want to find the integral for. So let's move down where we can see here. Okay, so my greatest p-value is going to be 1.5. And then we set our comparison equation. This is our comparison equation right here. It is going to be less than our integral. Okay, and in this case, let's figure out what our integral is here. Our integral from 0 to 1 of x to the 1.5, I can't plug in that 0, so I'm going to have to do a limit. and I'm going to do the limit as t approaches 0 from the right hand side if we need that, and the integral from t to 1 of x to the 1.5, negative 1.5, that's very important, dx. Okay, so I'm going to add 1 and then divide by that number. So when I add 1 to negative 1.5, I'm going to get negative 0.5. Divide by that number also. So let's come over here where we have some more room. And so we'll have negative 2 times the limit as t approaches infinity from the right hand side of x to the negative 1/2 evaluated from 0 to 1. So that's going to be equal to the negative 2 times 1 over the square root of 1 minus 1 over the square root of, oh, that's supposed to be a t. And then we need to take that limit as t approaches 0 from the right hand side. Okay, so if we have a negative 2, I'm going to pause here and calculate all of those. Okay, so I needed to evaluate this for t, for values of 0 to the right hand side. So I chose 0.000001. I did a couple of really small values like that, plugged them in for t. I was getting bigger and bigger values. So what this tells me is that the limit as t approaches 0 from the right hand side of this equation is going to go to positive infinity. So if this equation is less than our equation that we're looking at, this one right here, our interested one, if an equation less than this is diverging to infinity, then this one also is. So our less than equation diverges, which also means that our original equation also diverges. Okay, and that's it for examples for this section.